So yesterday we went over a bunch of Newton's second law problems related to systems containing multiple masses. All right, we're kind of getting that, and we worked on some kind of practice ones that were more like what were on our quiz here. And I think from your quiz you can see that sometimes even when a question is mathematically quite simple, okay, it can be, again, contextually difficult. Right? We have to be able to visualize the situation and see what's going on. That becomes even more evident when you run into a question like this. Okay, this is what we call a static condition question. Okay, what does static mean? Doesn't change. Okay, so this is a situation where the object's not doing what? It's not moving, which is weird. It's still a Newton's second law question, but the object's not moving. What do we need to remember about a situation where the object's not moving? Okay, there's no VI or VF. I'm thinking more from a Newton's second law perspective. There's no acceleration. If there's no acceleration, then there's also no what? There's no F net. That means all the forces add up to what? Right. Try this one. Knowing now that this is a condition where the net force is 0. All the forces add up to 0. Okay, so what we have is here's one of the buildings, okay, and here's the other building over here, right? The sign is hanging like this, right? So it's angled 55 degrees below the horizontal. So here's the horizontal, okay, and here's the cable. So this cable is holding the sign like that, and then there's a horizontal cable that goes across like this. All right, they're supporting the sign. So there's, what we're looking for here is the tension in this cable. Okay, so cable 2. This is cable 2, and this is cable 1. All right, cable 1 is pulling this way. Cable 2 is pulling that way. Yet the sign stays put. All right, there's a bit of vectors involved here. Okay. Think about which way or ways the cables can pull. All right, let's have a look at this one. So the sign's not moving, so we know all the forces add up to 0. That's the first realization we have to make. Okay. Then we have to think about why do they all add up to 0, or how do they all add up to 0. So let's identify the forces acting on this sign. Okay, so we've got obviously the first cable here, cable number 1, that's pulling this way. If it's pulling at an angle, it's pulling up and, okay, why is it pulling up? Because it's counteracting gravity. All right, so this is our vertical force, and it is counteracting this force. They are the same in magnitude, opposite in direction. Okay, why is this cable pulling this way? It's counteracting this cable. So this cable and this cable must also be the same. All right, now I don't know what this cable is, but at least I can figure out what gravity is. Everybody all right with that? Okay, so I'm going to figure out what gravity is. Okay, and this is 55 kilograms here. So we're going to go 55 times 9.81. All right, so our force of gravity is 539.55 newtons. All right, so that means this force is also 539.55 newtons. How does that help me? Oh, sorry, is it 35? Sorry, 35. Let's try that again. What is it? 343.35 newtons. Okay, 343.35 newtons. Okay, how does that help me now that it's right? Okay, I can find the hypotenuse, but I don't think I need it. Right, I can find this one. This is the one I need because the question wants me to calculate the tension in cable 2. And I know that this whole force is due to this cable. It's offsetting it. That's why the sign's not moving. Okay, is because this cable here that's angled is pulling just as hard to the left as cable 2 is pulling to the right. Okay, that's the, once we realize, okay, all the forces add up to 0 horizontally and vertically, that we can start figuring out some of those forces and then realizing their relationships. Okay, so I'm going to calculate this side using tan. Okay, I've got the opposite side of the 55-degree angle, and I'm looking for the adjacent one. So I'm going to go the tan of 55, okay, equals opposite over adjacent. So I'm looking for the adjacent side. So adjacent will be equal to the opposite side divided by the tan of 55. So 539 point, sorry, not 343.35 divided by whatever the tan of 55 is. That's where I got the 55 for the mass. I was looking at the angle. Okay, 343.35 divided by the tan of 55. Okay, so there's 240 newtons worth of force in cable 2. So I would say 240 newtons right. Okay. In fact, with that one, I wouldn't even have to put a vector on that. Unless it asked me which way is cable 2 pulling, then I would have to say to the right. But when it asks for tension, tension is just how tight is the cable. That acts in both directions. I would not technically have to write a vector on it. Okay, everybody with me on that? Okay, so this is kind of the vector nature of forces, okay, especially in what we call static condition questions. In any condition or any example where the object's not moving, we are dealing with a net force of 0 and thus a static condition example. All right. Okay, questions on that one? Okay, we did a couple like this yesterday. System questions, okay, with pulleys. This time, I have a 5 kilogram mass hung over a pulley. I have a 4 kilogram mass connected to it over the pulley, but sitting on a table where there are 32 newtons worth of frictional force acting on the 4 kilogram mass. So I want you to calculate the acceleration of the 5 kilogram mass. Okay, we did a bunch like that yesterday, so I'll give you a few minutes on that. Okay, so first step here, we got to identify the forces that are acting within this system. All right, obviously gravity is acting on the 5 kilogram mass. Right, m times g is going to give us 49.05 newtons worth of force there. Everyone okay with that? Okay, forces acting on the 4 kilogram mass, gravity, and what's that force? The natural force, normal force, reactive force, whatever. Okay, this and this are what? Equal. Okay, do they matter then? No, they cancel each other off. But it's important to just know that they're there. Okay, when we talk more about friction, that normal force will become more important. And then obviously, what force is this? It's friction. Okay, and we know that it's 32 newtons. All right, these are the only two forces then that matter in the movement of this system. Okay, so I'm going to simplify my diagram by saying I've got 9 kilograms worth of system mass being pulled this direction by 49.05 newtons and this direction by 32 newtons. That would be accurate. Those are the two forces opposing each other in this system. Okay, so then I've just got to find my vector sum of all forces. Okay, that'll be my next step. So it's m times a and the vector sum of all forces. So the vector sum of all forces will be 49.05 minus 32. So that should be 17.05. Is that right? Okay, so my net force is 17.05 newtons. All right, if I want to find the acceleration, then I go to m times a. F net divided by m. So 17.05 divided by what? 9. right? Remember, I've told you several times now that I will try to trick you by only naming one mass and seeing how many of you will divide by only that mass. Remember that this force is accelerating the entire system, right? So that's 9 kilograms. All right, so when we do that, we should get 1.9 meters per second squared. And what do I need to write on the end of that? Down, because I asked specifically about the 5 kilogram mass, which will be descending. All right, so that would need down on it. All right. Yeah, and I would actually have to say the magnitude of the acceleration in the question. As soon as you see magnitude of, then you don't have to worry about direction. Or of the system, then you don't have to worry about direction, unless the entire system is moving the same way. Like when we had those two boxes connected together and we were pulling them together, okay, then yeah, then the whole system would be forward or right or whatever it happened to be. Okay, most of the time in a system, there's differences. Okay, all right, is that making some sense? Okay. All right, we did one like that yesterday. We'll skip it. Okay. Calculate the tension in cable A. Right, so you got 120 kilogram mass. This is like that big speaker at center field, okay, at McMahon Stadium. Okay, if you've ever gone and watched the Stampeders play, okay, they got that big speaker that sits at center field, hangs there, okay, or the big scoreboard or whatever, right? Hanging by cables, so big heavy thing being suspended by cables, okay, 40-degree angles here, 100-degree angle in between them, right? See if you can figure that one out. So is this another static condition example? Yes. The weight, or sorry, the big mass there, the 120 kilograms, is not moving. So the net force acting on it is 0. Now, I asked you to find the tension in cable A. All right, so here's what we got to do. Let's identify the forces. Force of gravity is pulling downwards on the 120 kilograms. Okay, and so that's going to be 1177.6 newtons. Sorry, 1177.2? Sorry, not 0.6, 0.2. I was close. Okay, Newton. So that's the force downwards. Now, there's two cables, and they both pull diagonally, which means they both pull up. How much of that is each one holding? Exactly. So what I'm going to do here, okay, is make a triangle. I guess we can make it like this as well. Okay, this side here is going to be the vertical component of cable A. Everybody all right with that? How big is that? I'd like a more specific number. It's half of this number. Each cable's vertical component is half of the force of gravity. All right, so I'm going to take that 1177.2, divide it by 2, all right, and that'll give me 588.6 newtons. All right, I don't need to worry about the horizontal component because I don't require it anymore. I now have an angle and a side that will allow me to find the hypotenuse of this triangle, which represents the tension in cable A, which incidentally is the same as at cable B, right? Because their angles are all the same, their tensions are the same as well. Okay, so I take that 588.6, I'm using, that's the adjacent side, and I'm trying to find the hypotenuse, so that'll be using cos. Okay, so the cos of 40 degrees equals 588.6 divided by the hypotenuse, which is what I'm looking for. So to find the hypotenuse, I'm going to go 588.6 divided by the cos of 40 degrees, and that will give me the tension in that cable. So 588.6 divided by the cos of 40. All right, so we're looking at 7.7 times 10 to the 2 newtons, okay, would be the tension in that cable, right? I could say that's 50 degrees above the horizontal or 40 degrees from vertical if I wanted to, but it's a tension. Right? I don't actually have to put a direction on it.
Why is the middle thing here?
Oh, just to indicate to you that the complementary angles here would be like 50 and stuff. Actually, that didn't work out the way it was supposed to, but yeah. Was that what threw you? Okay, what it does is it also creates this triangle here where this angle would be 50 degrees. I drew it wrong. I don't know why I put 40 there, but yeah, no, this should have been 50 here. This should have been 40 here. Yeah, no, I drew it wrong. Yeah, you're right. I screwed you up. Yeah, as long as your method was right without my mistake in the drawing. Yeah. I don't know why I put the 40 in there. This should have been 90 is what it should have been in the middle, not 100. Yeah. Yeah, this should have been 50. Yeah, you're right. That should have been 50. And then this could stay 100. Yeah. Okay. No. If you used it the way I drew it, it worked. But yeah, if you did it the other way, you might have got a different answer. Okay, because if you said this angle here was 50, okay, then and you would have been right to say that angle was 50, not 40, you would have got a different number. Yeah. I'm assuming I had, well, these angles here, if I used this one, it would be 2. If I used 100, it would be 3. Yeah. So yeah, it would depend. I just drew that one too quickly, I think, without thinking about it, and I messed it up. Okay. Incline planes. Okay. Incline planes are another Newton's second law. And this is like, I love incline planes. I use them all the time. I've never not had an exam, or I didn't have one. Never not. That's double negative. Okay. It's like negative forwards. It doesn't work. Okay. Yeah. So incline planes are very, very common because they bring in everything. They bring in some vector stuff, and they bring in, like friction and all these other things. So they're a good example. If I put something on a ramp, okay, what will it do? Yeah, it's likely to slide down the ramp, right? As long as there's not too much friction, okay, or the ramp's not, the ramp is steep enough. What makes it do that? Gravity. Okay, yes, partly gravity, but gravity's pulling it which way? Down, straight down. Gravity can only act straight down. Gravity doesn't act down the plane, okay? But that's the way that the box will move, is that way. So that means the vector sum of all the forces involved is down the ramp. Okay, so what are the forces involved? Well, one of the forces we already said is gravity. Okay, gravity acts straight down. Then there's normal force. Okay, and which way does normal force act? Well, in this case, it doesn't. Normal force will act straight up when the surface is level. It's always going to act straight out from the surface. Okay, so it's going to act this way, right? So if I'm drawing a free body diagram, normal force would go up over here. But I'm going to draw the vector diagram. Okay, that's my normal force. Okay, and I've drawn it tail to head with gravity. Those are the two forces that are acting. We'll assume this is a frictionless incline for right now. Okay, those are the only two forces acting then. Everybody all right with that? If there's no friction, and I just plop a 10-kilogram mass on this ramp, it's going to slide right down, okay, right away. So my net force then is the vector sum of these two forces, which is right there, right? When I connect the beginning and the end, just like I would in any vector diagram. Okay. It's supposed to be perfectly parallel, but it's not quite, but it's supposed to be. So the vector sum of those two forces points down the ramp. All right. If friction was involved, okay, if friction was involved, that would be fine. Okay, we would just put it on the end here. Friction would act which way? Up. Right? Friction always opposes the motion. So if the box is sliding down the ramp, friction would act up the ramp. Right? And then my net force would be smaller. It wouldn't accelerate as much. Everybody okay with that idea? All right. But for right now, let's just assume that the ramp is frictionless. Okay. This force that acts down the ramp as a result of these two forces is called F parallel. okay? Because it is parallel to the plane, or it is the component of gravity acting parallel to the plane. All right. Can I calculate how big it is? I can, as long as I know this and that. All right. So I know the mass of the box. I can calculate the force of gravity. The force of gravity will be 98.1 newtons. Okay. If this angle is 30 degrees, what's that angle? 30. That's the offset between gravity and normal force, right? Normal force is going to be 30 degrees offset from straight up and down, okay? Because that's the angle of the ramp. Okay, everybody with me on that one? Right? These are similar triangles, right? So those two angles would be 30 degrees, okay? Normal force always acts straight out from the surface, and this surface is angled 30 degrees. All right, so we've got those two forces, okay? And sorry, we've got that force and that angle. Now I can calculate F parallel. F parallel is opposite the angle, and I have the hypotenuse. So what trig function do I use? Sine. Okay, so the sine of 30 degrees times the force of gravity, which is the hypotenuse, will give me F parallel. So it'll be 49.05 newtons. Okay. All right. Since there's no friction, that's my net force. Can I calculate how quickly my box will accelerate down the ramp? Yes. Okay, so we go back to this. Right, so we just did the sum of all forces, okay, the vector sum of all forces, and now we're calculating acceleration by going 49.05 divided by 10, 4.9 meters per second squared. Down slope, down ramp, downhill, okay, whatever it happens to be, right? Why do I not write down? Because that's straight down. Down is straight down, okay? If you're dealing with an inclined plane, you are not accelerating down unless you fell through it, okay? As long as you're going down the plane, you need to write down the plane. All right, so this little triangle here, okay, is the important part of being able to solve any inclined plane problem. All right, so this angle and this angle are always going to be equal. The hypotenuse will always be gravity. Normal force will always be this side, and F parallel will always be this side. Right? Now I want you to see what happens here if I change the angle. Right? If I change this angle here, okay, so I lower the ramp, okay, then FG stays the same, but F normal will get bigger, and F parallel will get smaller until it's level, and there'll be no F parallel because Fn and Fg will be equal. Okay, the steeper I make it, okay, the smaller normal force gets, the bigger F parallel gets. Right? The steeper the hill, the faster it goes down the ramp until the hill is vertical, in which case there's no F parallel because there's only gravity. Right? It'd be falling then instead of sliding. Right? Does that make sense? All right, so that's how an inclined plane works. We're going to run into lots and lots of those. Okay. All right, I'm going to stop introducing new stuff now for a little while. Now we have lots of different things to work on and think about. But guys, I'm only about halfway through all of the different situations that might come up. Okay, and I've gone over a lot. Right, so there are lots of applications here, okay? And we haven't gone into when there's friction involved and you're pulling the box up the ramp, okay? Because, I mean, what do you use a ramp for? No, usually the inclined plane is the simplest tool, okay? It allows you to move large masses using less force, okay? If I want to lift a box from here to the top, I have to go completely against the force of gravity. If I push this box up the ramp, I can use less force because the ramp supports a lot of the weight, the normal force here. Everyone with me on that? I don't do any less work. It's the same amount of work to push it up the ramp and lift it to the ramp because I change its energy by the same amount. Okay? Reason being, this is longer. right? I use less force over a longer distance, more force over a shorter distance here. Okay, same amount of work to get there, but I can use less force, which means I might be capable of getting the box to the top of the ramp. Okay? That's the whole idea behind the inclined plane. That's why the Egyptians, or how the Egyptians built the pyramids. Right? They did not have help from aliens. They had lots of sand with which to build ramps and lots of slaves to push rocks. Okay? Yeah. All right. Everybody with me on the inclined plane stuff? Okay. Because if you're not, you'll be an inclined plane wrapped around an axis. Yes. What's an inclined plane wrapped around an axis? A screw. You'll be screwed. Think about it. You take an inclined plane and you wrap it around an axis. It's a screw. That's how screws work. Okay? A screw is a ramp that allows you to push it into wood. Okay? By using a ramp instead of pounding it with a nail or a hammer. Not pounding the nail with a hammer. Don't pound it. Yeah, not the other way around. Doesn't work very well. Okay. I want you guys to try in the workbook a couple of questions here. I'm just going to list them. Okay, so for question number 1, we've got a tow truck that's pulling this car. Okay, so the car is 1,500 kilograms, okay, and it's being pulled at an angle, right, 45 degrees with the road. All right, there's 2,000 newtons worth of friction, worth of tension in the cable. Now, it doesn't mention anything about lifting the car, just about pulling it. So is the car moving vertically? Okay, then that means I don't care about this vertical component. It's just going to cancel off gravity. Okay, gravity and normal force and that force vertical will all cancel out to 0 because the car is not moving vertically. It is, however, moving horizontally. All right, and it does tell us that friction is opposing with 500 newtons worth of force. Okay, so we're looking for the acceleration of the car. We have to find the horizontal component of this 2,000 newtons. So that'll mean going cos of 45 times 2,000. All right, now I've got my force horizontal. I can subtract friction. That'll give me my net force, which I then divide by the mass of the car. Okay, 0.609 meters per second squared. All right, we will see you guys tomorrow.